Have you ever pondered over how sophisticated electronic gadgets are engineered? How does a basic concept evolve into an elaborate electronic phenomenon? The solution is nestled in the realm of VLSI design. VLSI, which stands for Very Large-Scale Integration, refers to the technique of fabricating an integrated circuit by amalgamating millions of transistors into one chip. This task might seem overwhelming, but the VLSI design flow simplifies it into achievable stages. Following the introduction to VLSI design, we delve into the first significant step, transitioning from specification to architecture. This phase involves defining the requirements and constraints for the integrated circuit, IC, or system on a chip, SoC. This includes detailing its functionality, performance, power consumption, and area constraints. We then establish the high-level architectural plan. This stage is a crucial intersection where theoretical understanding meets practical implementation. We use a hardware description language, HDL, like Verilog or VHDL, to create a high-level design representation of the IC or SoC. This step captures the logical behavior of the design. Once the design is captured, we move to functional verification. This is where we ensure that the high-level design meets the specified requirements. We simulate its behavior using hardware simulation tools to ensure that the logic behaves as intended. This verification is vital to ensure that the design's functionality aligns with the initial specifications. After the design is verified, we proceed to synthesis. This step involves translating the high-level design into a gate-level netlist, which consists of logic gates and flip-flops that implement the design. This step maps the design to actual hardware components. Next up is design optimization. Here we optimize the gate-level netlist to meet various design constraints, such as power consumption, timing, and area. This step helps improve the design's efficiency and performance. Finally, we transition to physical design. We place the logic gates and perform routing to create the physical layout of the IC or SoC. It's crucial to ensure that the layout adheres to timing and area constraints. In this scene, we'll delve into these steps in greater detail, providing you with a comprehensive understanding of how we move from system specifications to an architectural design plan. Stay tuned as we demystify the world of VLSI design. The journey begins with system specification. This phase is all about defining what the system is intended to do. It's the blueprint, the roadmap, that outlines the performance, physical, and economic constraints of the proposed device. Once the system specification is clear, the next step is architectural design. This is where the system is partitioned into several modules based on the specification. Each module is defined by its functionality, and the interaction between them is established. Following the architectural design comes logic design. This stage involves converting the system specifications into a logical structure. In simple terms, it's about defining how the system works, using logic gates and flip-flops. Next up, we have circuit design. At this stage, the logical structure from the previous step is converted into an electrical circuit. This involves deciding the circuit technology and the type of devices to be used. Now, the design is ready to move into the physical design phase. Here, the circuit design is transformed into a geometric representation. It's all about placing and routing the components on the chip. After the physical design, the chip is ready for fabrication. This is where the actual integrated circuit is built. It's a complex process that involves several stages, including photolithography and etching. Once the chip is fabricated, it goes through testing and verification. This stage ensures that the chip functions as intended and meets the system specifications. Any discrepancies are identified and corrected. Finally, after rigorous testing and verification, the chip is packaged and ready for distribution. The packaging protects the chip and provides the necessary connections to the outside world. To summarize, the VLSI design flow is a systematic process that transforms a system specification into a tangible, functional device. It involves several stages, including system specification, architectural design, logic design, circuit design, physical design, fabrication, testing and verification, and packaging. Each stage has its own significance and contributes to the overall functionality and performance of the device. Understanding the VLSI design flow is crucial for anyone interested in electronics, as it provides a structured approach to designing complex electronic devices. It's an intricate dance of logic, design, and technology that brings our electronic devices to life. And that, my friends, is the fascinating world of VLSI design and design flow.